All right, super. Thank you all for coming. Let's just very briefly review what we talked about last time, which is retarded propagators. So we talked about the propagator, which is the matrix element of the time evolution operator and the position basis. And the retarded propagator, literally all we do is we throw on a theta function, which forces the future time to be later than the initial time. And via some manipulations, we were able to show that this retarded propagator is precisely the Green's function for the time-dependent Schrödinger wave equation. And we like Green's functions because they allow us to solve very general problems in PDEs. Very good. And I sort of did a much better job of the sort of active versus passive stuff that I messed up in terms of the labeling last time. I corrected the notes and put those up online. I feel like that's sufficient for covering that area. Okay, super good. All right, so let's proceed. Today we will, as the last class, we'll do a couple of really nice things. One is the resolvent, and then the other is Bell's inequality and the EPR paradox. And the purpose of talking about the resolvent is to give you insight into a complete reformulation of quantum mechanics away from the four postulates of quantum mechanics we had discussed at the beginning of the class, and replacing essentially two of those postulates with path integrals. So this is more of a derivation that is of conceptual interest. It's a derivation of conceptual interest. Okay. All right. So as promised, we're working towards a complete reformulation of quantum mechanics using path integrals. Perhaps as an analogy, in classical mechanics, you start with F equals ma as the fundamental postulate. And then one would like to have a complete reformulation of classical mechanics, for example, with Hamilton's principle. And for details that we could talk about ad nauseum in a different setting, that's not actually a complete reformulation, but it does give you an enormous amount of insight to think about the problem in a different way. And that's the same thing that's happening here, except it is a complete reformulation. Where we'll replace postulates 2 and 4 using path integrals. All right, great. Oh, good question. Jeez. You know what? I honestly, I had to look it up myself. I had to look up what the postulates were to figure out which postulates 2 and 4 were. So postulate, I think this will, no, because I'm sharing the screen over there. So postulate 2 is that observables are represented by Hermitian operators, and the commutation relations between operators is given by the direct quantization condition. And then postulate 4 is a time evolution by the Schrödinger wave equation, or not Schrödinger wave equation, but the Schrödinger equation. And really what I would like to emphasize is that everything we've been doing so far, what I would call canonical quantization, where we are thinking about operators, one can rather think about integrals over numbers. So from the very start, you're working with numbers, which are easier objects, but path integrals, which are harder objects. As my old supervisor used to say, there's always a conservation of pain. Yeah. Okay. Good. And just, I think I made it clear, but this is really, one could make this concrete, and if this is a longer course, and we had more time, we could have you explore in real detail this complete reformulation. I just want to expose you to the idea, the concept of the reformulation. And maybe I could point out that you might be asking the question, what is the value of this reformulation? I would say the major value is that the path integral is an integral over the e to the I action. And so it's a formulation for which symmetries can be embedded from the very start. And Feynman, when asked to describe the history of 20th century science, he said, one, the world is made of atoms, and two, the world is determined by symmetries. So our modern formulation of physics is based on symmetries. So there's an enormous value in formulating the problem where symmetries are explicitly respected at step zero. Yes.
What makes the action embedded to describe symmetries?
Because what we take as the object that is going to be invariant under symmetries is the Lagrangian rather than the Hamiltonian. And the action is simply the integral over the Lagrangian. Good. Good question. Thank you. Okay. So in order to make this replacement, we'll need a way to extract eigenvalues and eigenfunctions from path integrals. So path integrals are very adept at giving you expectation values. And that is one thing that we would like to have as a prediction for experimental measurements. But we'd also like specifically to know what specific outcomes could be, and what are the specific probabilities of those outcomes. And those are therefore eigenvalues and eigenfunctions. And at least in terms of energy eigenvalues and energy eigenfunctions, the resolvent provides the tool with which we can extract those quantities. And I recognize that this grammar is not great, but you get the idea. And then just to throw words out into your brain, the resolvent is often valuable from a more mathematical perspective. Just a second, more mathematical perspective in quantum mechanics, and think about quantum mechanics because it's what's known as a compact operator. So it's something that for which the spectrum does not go out to infinity. And you'll see this in a moment in terms of how it seems more compact, that it's compact. And yeah, just know for technical reasons that many mathematical physicists consider the resolvent rather than say the Hamiltonian. Yes.
Sorry,
did I not?
Is that red thing in the recording?
Yes. Well, that red thing up top says that my screen is sharing. This is telling me that it is recording. Yeah, great. Good. Super. All right. So let's define the operator version of the retarded propagator. Yeah, and because I'm recording, I'm throwing it to YouTube. Please watch. Bump up the views. It makes me feel good. It really does. So please do that. Yeah, I think the second lecture, for reasons that are totally unclear, has like 70 views, which I think is amazing. The more recent ones, it's like a few. Like, all right, fine. I think the algorithm served up my lectures to some random people. Oh, great, yeah. Keep it up. I love it. All right, so writing the resolvent, or not the resolvent, the propagator as an operator. So I'm just saying I have the time evolution operator, and then I'm just slapping on a theta function. And one can see that if I take I partial t of this retarded propagator. This is I partial t of the right-hand side. And we know from the Schrödinger equation, I partial t of the time evolution operator is a Hamiltonian. And then product rule, the time derivative acting on the theta function gives me a delta function. Perfect. Now, this delta function tells me that the only contribution I will ever get from this term is going to occur when t equals t0. And so I'm able to take this time evolution operator, which is in principle evaluated at times t and t0, to only be evaluated at t0. And what is the time evolution operator from t0 to t0? It's just the identity. Exactly. Very good. And so what we've learned, if I do some rearranging, is that the Hamiltonian at time t minus I partial t acting on the retarded propagator operator is equal to minus I delta t minus t0, and then the identity operator. So I just pulled the I partial t to the right, and I took the I delta to the left, and I get the final result here. What does this mean in terms of an interpretation of this retarded propagator operator? It's a Green's function. You seem so sad. No, it's exactly right. So this tells us then that this object is a Green's function for the operator form of the Schrödinger equation. And that should come as no surprise, because we showed that if we take the matrix element of the left-hand side, we'll get the retarded propagator in the usual form that we're used to. And on the right-hand side, we'll get the Dirac delta function between x and x0. And then we'll have reproduced what we derived last time and what I reminded you of earlier today. Good. Any questions there? Okay. So I'm going to do some manipulations, and they're perhaps not going to seem obvious why you would do it, but the result hopefully will be compelling. So maybe just hang in there for a minute. So let's consider the Fourier transform. Let me define as equation 1 that definition of the retarded propagator operator. So let's consider the Fourier transform of 1 with respect to t. And our manipulations will only really make sense for a time-independent Hamiltonian. So we'll use that. And for convenience, because the system is time independent, there's a symmetry, there's time translation symmetry. We can set t0 to anything. So what do you think is a good value to set t0 to? Let's just make it 0 exactly. Life is hard enough as it is. Let's not make it harder for ourselves. All right. Then define the retarded resolvent GR by GR of E plus I epsilon is minus I integral minus infinity to infinity dt e to the I E plus I epsilon t retarded propagator operator t. So I've dropped the T0 in my retarded propagator operator. The object on the right is an operator. The object on the left is an operator. There is this epsilon, and that's a convergence factor. So the epsilon, little curly epsilon in 2 is a convergence factor. So we have that 1 is much, much bigger than this curly epsilon, but epsilon is strictly greater than 0. 1 often takes the limit. Curly epsilon goes to 0 from the positive side at the end of various calculations. And I'd say that many authors leave off the plus I epsilon as implicit in equation 2. So that's just a warning if you're reading up on this elsewhere. Often people will just write GR of E, and there's just an E up here. But to make things converge, one needs to add the plus I epsilon. And it's a plus I epsilon to mean that one is integrating up to positive infinite time. So these I epsilons that we've talked about already in terms of in the retarded propagator, they are key to boundary conditions. Are we interested in propagating solutions forward in time or propagating solutions, for example, backwards in time? And we'll see a specific example of that in a moment. Let me pause for questions. Yeah. Hey.
Is that capital E, does that have any the physical significance at the moment?
At the moment, no.
Okay, so it's just right now a choice.
Yes, but the letter is suggestive. Good. Yeah, exactly. Other questions? All right, great. So what does this thing look like? All right, so let's examine the Hamiltonian hitting this resolvent. It's a resolvent operator. So just from the definition, minus I integral minus infinity to infinity dt e to the I E plus I epsilon t. Hamiltonian hitting the retarded propagator operator. Now, this retarded propagator operator from, I guess, I didn't name it as an equation. We see that the Hamiltonian hitting the retarded propagator operator spits out a minus I delta identity plus I partial t retarded propagator operator. So this gives me a minus I delta t identity operator plus I partial t retarded propagator operator. Okay, so it's easy enough to evaluate the delta function with time. And so we just get a minus identity from the first term. And we get plus an integral from minus infinity to infinity dt e to the I e plus I epsilon t partial t retarded propagator operator. The i's all cancel with the -1. To make some progress, you know, if you're faced with something that looks like this, a nice thing to think about is always integration by parts. So let's do an integration by parts. So we'll get a total derivative of the two terms, which will spit back out an e to the I e plus I epsilon t retarded propagator operator time t evaluated from minus infinity to infinity minus the integral minus infinity to infinity dt partial t e to the I e plus I epsilon t retarded propagator operator, like so. Now, remember that this, oh my gosh, erased too much, but it's fine. This retarded propagator operator here, this thing has a theta function of t in it. So when we evaluate this whole object at minus infinity, this is 0. So 0 by kr t ortho theta t. Then, so long as this retarded propagator operator is not horrendously bad behaved, i.e. blowing up exponentially fast at future time, notice that we have a plus I, and then a plus I, something epsilon, which is positive, and then t, which is then infinity at the upper end. Then there's e to the I e t, which is some oscillatory thing, and the kr of infinity, which, as I said, we're assuming is at worst blowing up polynomially in time. And if that's the case, then the upper bound is also 0. And so this is the effect, the explicit effect of the convergence factor. And it's very important that it's a plus I epsilon. If this is a minus I epsilon, we wouldn't be able to kill off this term at plus infinite time. If we wanted to go backwards, for example, so if we had, for example, an advanced propagator operator, which looked like theta of minus t, then we could kill off the upper bound of t. And if we had a minus I epsilon, we could kill the lower bound. So the plus minus I epsilon is really intimately connected to your boundary conditions. Yes?
I think that's great. It's sort of, we're going to send t to infinity now, then later we can send epsilon to 0. So like, we sort of have to argue that we can do that.
Yeah. So that's, I think, a fair point. I'm being very physicsy here in terms of evaluating these limits, right? So if I'm doing this in a math class, I would have to say that I'm really taking the limit b goes to b and evaluating this at b, and that's nested inside a limit epsilon goes to 0 from the plus side, and I cannot reverse the operations of those limits. Absolutely, yeah. But I'm unaware of any subtleties that are related to that. So we're just going to always, I'm going to try to be explicit in keeping a limit epsilon goes to 0 always hanging around. But yeah, the limit epsilon goes to 0 is at the very last step of any of these calculations. So that's going to be fine. I think there's a question here, then here.
So you said that became exponential is polynomial.
Yes.
How do you see polynomial? Because I'm just thinking, I'm thinking the time division operator, time independent Hamiltonian is exponential as well.
It's an exponential, but it's actually a phase. So it's just zipping around an absolute value of 1. So that's not a problem at all.
I didn't quite fully get the argument for why the time propagator runs into the 0.
Because we define this operator as proportional to a theta function.
Yes. Okay, that makes sense to me.
Good, great. All right, yeah, super, very good. Last questions. Wonderful. Okay, so this rightmost term, let me just be lazy with my writing. So this is going to give me an e plus I epsilon, and then a minus I, integral minus infinity to infinity dt of this retarded propagator. Oops, I missed a crucial part, which is the Fourier bit, e to the I, e plus I epsilon t. And this piece here is precisely the resolvent that we had defined before. This retarded resolvent. Okay, so putting the pieces together, Hamiltonian acting on the retarded resolvent gives me -1 plus the retarded resolvent again. So rearranging, oh, sorry. Oh, gosh, I missed a crucial part, which is the e plus I epsilon. Sorry. I'm going to assume that you would have caught me on that in a moment. Tion's way on the ball. Very good. Thank you. All right. So that tells me then that e plus I epsilon minus the Hamiltonian operator. I guess there's implicitly a 1 multiplying this e plus I epsilon, acting on retarded propagator, sorry, the retarded resolvent is equal to 1. What does that tell me? It tells me that this retarded resolvent is e plus I epsilon minus the Hamiltonian, all under 1. So nothing fancy, I'm literally just dividing. This is, one might say, a formal derivation, right? What does having an operator in the argument of a denominator mean? And we can always define these things in terms of Taylor expansions. Good. Further, as promised, we can see how this operator is much more mathematically well behaved than the Hamiltonian itself. Normally, if we have, for example, the infinite potential well, simple harmonic oscillator, the spectrum of the Hamiltonian is unbounded and go out to infinity. But you can see here that the spectrum for this operator is generally going to be bound. And so for mathematicians, that's very valuable. You get a number of nice mathematical properties, a number of nice theorems that you can then use. Good. Any questions on that? Yes.
Sorry, so the e plus I epsilon has the eigenvalue
Yeah, one could be a little bit more explicit. And so then you'd say,
that's the inverse.
I'm sorry, that's the
E plus I epsilon 1 minus the Hamiltonian extended inverse of GR.
is the inverse of GR. It's not the inverse, it's 1 over. So just being, yeah, so sometimes the inverse of an object is 1 over the thing, but you know, the inverse sign is not 1 over sign, for example. Yeah. Was there a question over here? Okay.
Just to be clear, this argument would work for any argument of the retarded resolvent GR, but it needs an I in the argument.
I'm not entirely, so let's try to be more clear in your question, I think. So the manipulations that we did here, I think you're basically asking, like, I have an argument here.
Yeah.
Can that argument be completely general?
Exactly.
And the answer is no. We absolutely need to have, you could say, okay, often this is just written as Z. And so long as the imaginary part of Z is positive, we're fine. Yeah. So, okay, that's actually, that would be nice. So often one writes GR Z is equal to Z minus Hamiltonian, Z1 minus Hamiltonian, where the imaginary part of Z is strictly greater than 0. Yeah, good. Other questions? Looking at Rachel, because Rachel often has good questions and often has questions. All right. All right, great. I'll continue then. All right, what about the matrix elements of this object? Well, let's examine X, GR, E plus I epsilon, X0. So this is X. And then, you know, forgive me for dropping the identity there. I think we've clarified that fully. That's, I think, a reasonable shorthand. This is not so easy to look at or to deal with. So let's insert a 1. Let's in particular insert a 1, which is a decomposition in the energy eigenstates. There might be a continuous part of the spectrum, and then there'll be an integral. You know, let's just write it as a sum for now. What is the result of acting with this identity onto this retarded resolvent?
HM.
On the right track, yes. So these are energy eigenstates. And so the Hamiltonian is going to, as an operator, will be replaced by the eigenvalues. And the eigenvalues are En. Right? So this E, so in fact, let me make this perhaps a bit more clear. So we're asking for some function. I think I'm going to run out of room. So the matrix element is a function of E plus I epsilon, and then X and X0. So one is going to be able to freely, you can tell me, you know, my X0 is 3 meters and X is 5 meters. And then you could ask me to plot for you this function as a function of E, just scan over E. And one of the questions that we would like to answer is what happens? What's the result of that scan? That scan over E. Okay, we'll get there in just a second. So this is therefore going to be a sum over N of X En, En X0 over E plus I epsilon minus En. And what's the numerator? Well, the numerator is precisely the energy eigenfunctions for the nth state as a function of x, and then the complex conjugate as a function of x0. So I believe we're up to, my notes say we're up to equation 4. So maybe, yes, I think I wrote that as equation 3. So this is equation 4. Now, depending on who has taught you sort of PDEs, which is to say electrodynamics or electrostatics, so equation 4, in principle, should look familiar. And this is not casting any aspersions on anyone who's teaching really, because we all have limited time. There are limited topics that one can cover. But an important topic in PDEs is what's known as the eigenfunction expansion of a Green's function. So if you'd like to read up more on this, Jackson's E&M book, 3.12. So I would say that this is like how we rederive the Fourier transform function in terms of thinking about a function as a vector in a function space, and think about the function in various bases, and interpreting that as the well-known Fourier transform. And this, I think, is in a similar way, is we are rederiving this general result of PDE theory, Green's function theory, from the perspective of quantum mechanics. If that's helpful, it's helpful. If it's not helpful, forget it. Okay, but in terms of the quantum mechanics, 4 tells us that the resolvent, the retarded resolvent, contains all the information we seek. So in particular, the energy eigenvalues are given by the poles of equation 4. Pole is a technical term from complex analysis. All it's saying is that, as I said, we could think about scanning this G as a function of E. Where does this thing blow up? Where does it go to infinity? Right? It goes to infinity when E is En. And those ENs are precisely the energy eigenvalues of the problem. And you see why this plus I epsilon is so important. Because it means that when E does hit En, E being a real number, En being a real number, this doesn't become actually infinite. It just becomes very, very large. And the second point is that it gives us the energy eigenfunctions. Sine of x. Yes.
I'm confused how there's an I in the whole, because you've got a complex number minus a real number.
Yeah, so if we consider E to be, if we consider E to be complex,
Oh,
then it's exactly a pole at E minus I epsilon.
yes, okay, great. I just, okay.
I think we've mentioned this once or maybe several times. It's basically always a good idea to complexify everything in the kitchen sink. But yeah, So if you want like a formal mathematical comment, yes, we complexified E. From the physicist perspective, E is going to be real because the Hamiltonian is Hermitian. And we're just looking for where this thing gets large. Yeah.
Why are we assuming that the energy basis is discrete?
We aren't necessarily. We could say that this is an integral dE, psi E x, psi star E x0 over E plus, let's call this a tilde. Like so. And in particular, in your homework, you will work with you'll compute the resolvent for the free particle where the spectrum is continuous. Yeah, good. One just has to be a little bit careful because this E is the E of the resolvent, and this E twiddle is the quantity that's being integrated over. And it can be, from personal experience, it can be not necessarily confusing, but one can trick oneself accidentally. Okay, great. Any last questions? This brings us to the close of the resolvents, where, as promised, we were able to say with the path integral, compute the retarded propagator. And then we, in air quotes, only need to compute the Fourier transform of the retarded propagator to extract the energy eigenvalues and the energy eigenfunctions. Good. Air quotes doing a lot of heavy lifting there. Okay, great. Let's then continue to Bell's inequality and the EPR paradox. Have any of you heard about the EPR paradox and or Bell's inequality? One person has, two. Okay, so a little bit of knowledge, not necessarily everybody, totally fine. So in a 1955 paper, Einstein, Podolsky, and Rosen pointed out that the formulation of quantum mechanics in terms of states and the postulate of wave function collapse they would say made. I will use a slightly softer phrasing, which is appears to make quantum mechanics non-local. I.e. a theory that violates the postulates of special relativity that no two events with a space-like separation may influence each other. Okay. So this is bad. Einstein made a lot of progress in assuming that the fundamental, most fundamental principle of nature is that nothing travels faster than the speed of light. Figured out the precession of the perihelion of Mercury as a result. Incredible achievement that a 400-year-old mystery is solved. So he really likes special relativity. And his conclusion is that quantum mechanics must be wrong. So let me first point out a thought experiment that's in the spirit of what they talked about in the paper to show you why they thought the special relativity was violated. Oh, yeah, that would make, thank you. I can't read my own chicken scratch. 35. I was thinking like, man, 55 was pretty late. Like pointing this out, like they were working on field theory, like, okay, but all right, whatever. Notes must be right. I wrote them down. I mean, it's like I'm anchor man, right? I just write whatever is on the screen. Okay, so in particular, consider a simple experiment in which pi 0 goes to an e plus e minus pair. Has everybody heard of a pion? Good. The relevant point is only that a pion is spinless, and electrons do have spin. So since the pi 0 is spinless, and spin and angular momentum is conserved, the resultant state must be a singlet. So our final state must be 1 over root 2. And then if the positron has plus spin along the z direction, then the electron must have minus spin, and we get a minus the possibility that the positron has minus spin in this direction, in which case the electron must have plus spin. Everybody's happy with that. I don't know if you, I kind of vaguely recall that you have not done addition of angular momentum before. So the idea of singlet triplet. Okay, good. We're not going to rely on any like huge amounts of detail. Like, if you just have the idea of like singlet triplet, that I'm looking at a direct product, which we've also covered in this class, that's sufficient. Okay, good. So this tells us then that the expectation value of the spin operator is 0. Now let's suppose that in our experiment, we let the E plus and E minus, well, suppose that the pi 0 start off at rest. And we allow the E plus and E minus to fly off in opposite directions. For an arbitrarily long amount of time.
starting off at rest, you saying that in the lab frame, it has no velocity.
Sure. Pick a frame where the pi zero is at rest. Sure.
That's
Yeah,
what, that's what you're saying, take the frame in which it's at rest.
Yeah, and that's where our experiment's gonna be built. Yeah, yep. I feel like you put it actually better than I did. Yeah, good. Let's choose that in our lab frame, pi zero is at rest. Good. All right, so these things go off. Now, say that this experiment happens someplace halfway between the Earth and Mars. And these things fly off to Earth. Say the positron goes towards Earth. Dora measures the positron spin. Angelia is on Mars, and she's going to measure the electron. Now, as soon as Doron measures the spin of the positron, say you measure spin up, what is the result of Angelia's measurement? Spin down, right? That's the problem. That instantaneously, as soon as you, Doron, make that measurement, the wave function is collapsed, and that's going to influence what Angelia thinks. Right. So there's an instantaneous change across space-like separations. Okay, good. So suppose we measure spin of E plus. Now we collapse the wave function and immediately know what the result of any future measurement of E minus will be, no matter the distance. Emphasis on immediate. So I have written down a derivation, right? So if we have we're asking what is the probability of measuring, say, the E minus having spin down, given that we have measured E plus in the plus direction. So in general, a conditional probability is a probability of A, so probability of A given B is the probability of A and B divided by the probability of B. Now, in general, the probability of one thing happening when there are two things around, right? So what's the probability of measuring E plus to be positive? Well, it's a probability of measuring the E plus to be positive and the E minus is negative, plus a probability of E plus is positive and the probability of the E minus is also positive. So this is just 0, and so this is equal to 1. Probability of Z minus given that Z, Z plus, given that Z E plus is plus, that's similarly 0. Just slightly formalizing what we talked about. And if you want, you could go in with this particular state, and you could write down these probabilities as amplitude modulus squared. Good. So since one has access to information at space-like separations, EPR concluded that quantum mechanics is an incomplete theory so this is the EPR paradox. Well, I think I went around logically the wrong order. So since one has, all right, let's try this one more time. Sorry. The apparent access to information at space-like separations given the postulates of quantum mechanics is the EPR paradox. So one could resolve the EPR paradox if quantum mechanics is an incomplete theory. Right, so historically, late 19th, early 20th century, people looked at the equations of motion, Newton's equation, and said, I guess the way we would formulate this in a modern language is, F equals ma is invariant under Galilean transformations. Max's equations is invariant under Lorentz transformations. There is a irreconcilable tension, irreconcilable difference between the symmetry groups of the equations of motion for objects and the equations of motion for the electromagnetic field. And one way of formulating the question from that is to ask, do we need to make the electromagnetic field invariant under Galilean transformations? Or do we need to make Newton invariant under Lorentz transformations? And Einstein's position was we need to make Newton-Lorentz invariant. And he got a lot of mileage out of that. And so in this sense, he and his co-authors did the same thing. Said there is an irreconcilable, in their minds, an irreconcilable difference between the postulates of special relativity and the postulates of quantum mechanics. History has shown there's ever a discrepancy between Lorentz invariance and something else, Lorentz is going to win. So they said, how can we come up with a theory that looks like quantum mechanics? It's still going to seem probabilistic for an experimentalist, but that there's something hidden going on underneath the hood that, for example, when the pi0 decays, when they are causally connected, at that instant that the pi0 decays, the E plus knows already what its spin will be when it's measured. And therefore the E minus will also already know what spin it will be when it is measured. We can do this measurement many, many times, and so there's some kind of probability distribution for this hidden variable, which we may not have access to, but nevertheless, there is some deeper deterministic theory, local deterministic theory. Good. So if QM is an incomplete theory, so i.e. if there if there's a local invariable theory. Local being synonymous with causal, and then hidden variable theory we'll explain in just a moment. So, i.e., if there were some variables and or functions in addition to the state of the system, that provided a quote unquote complete description of the system. By assigning values to the observables prior to their measurement. Locality is preserved in a hidden variable theory. Because the E plus and E minus in air quotes know what spins they will have when they are observed. And they'll know this immediately after the pi zero decays. When the E plus and E minus are causally connected. Question so far. This also comes into the, Einstein, God does not play dice, right? So he really objected to this idea that the fundamental theory of nature is probabilistic. So he's saying, look, we've got quantum mechanics. It appears probabilistic and non-deterministic, but somewhere deeper down, God's not actually playing dice. We just don't know it yet. Okay, so Bell's inequality, which we'll talk about in just a second, is an inequality that any local hidden variable theory must obey. And it's an inequality that quantum mechanics explicitly violates. One may, well, let's put it this way, experimental measurements show excellent agreement with the predictions of quantum mechanics. I.e. nature violates Bell's inequality. And there can be no local hidden variable theory. We are stuck with quantum mechanics. So we'll go through in a moment the quantitative derivation of Bell's inequality, but I want to stop with that qualitative conceptual overview. Yeah. Super sad that Bell died before he got the Nobel for this. It's incredible. Yeah. Yeah. Yeah.
Does time build variables or physical
No. Let's come back to that. I feel like I'm in a good flow, and let's come back to that. It's a good question. Yeah.
So you've told us that what doesn't resolve it. Can you tell us something that does resolve it? Or is it?
Yes. We'll also cover that at the end. Good. Good questions. Great. All right. So quantitative derivation of Bell's inequality. So our big picture is try to exploit the triangle inequality. I'm trying to give you, or I'm giving you this big picture idea because I'm going to write down a bunch of stuff and show you that you get inequality and trying to motivate why you would construct this in the first place, beyond simply that Bell was brilliant and deserves a Nobel Prize for this. Okay, so instead of measuring the spins of the E plus and E minus along the Z direction, let's allow for a more general measurement. So suppose that the spin of the E plus is measured along the A vector direction. I have an underscore that I'm using instead of the over arrow. I must have a reason for doing that at the time. So I'm tempted to give it an over arrow, but I suspect that if I were to do that, I'm going to run into some issue later, and I don't want to mess that up. Okay, so measured in some direction, A vector, and the spin of the E minus measured along the B vector direction. So in the homework, it's an optional problem. One can show that the expectation value in quantum mechanics, given that one has chosen a direction A and chosen a direction B, that the expectation value, given our final state being in this singlet configuration, So I've got the expectation value, the bra and the ket are the same state, that singlet state. And I'm taking the dot product of my A direction with the spin operator for the E plus and the B vector direction dotted with the spin operator of the E minus. So these are operators. And what you can show is that this is explicitly equal to minus A vector dotted to B vector. So i.e. the measurements of E plus and E minus are correlated in a very specific way. We knew that already. We said that if we were to measure it, the E plus and spin up, then we know immediately that the measurement of the E minus is spin down, right? So if A is the plus Z direction, B is the minus Z direction. And then we get the expectation is just 1 in this correlated measurement. But we're just allowed to be more general. We have A and B here. Okay, good.
So this expectation value is you will have product expectation. Products.
So it is, well, it's not, so there's a dot between the direction of measurement for the E plus and the spin operator on the E plus. There's a dot product between the direction measured for the E minus and the spin operator for the E minus. And those two operators are direct producted here. It's saying that the number that you get out from this mathematical expression is equal to this. And the idea is that, yes, so taking the people we had before, so Doron measures the spin of the E plus on the A direction, he's going to get plus or minus. And Angelia is going to measure E minus on the B direction, is going to get a plus or minus. And then, yes, those are going to be multiplied. I'm going to do this many, 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 many times and average that. The average should be, well, quantum mechanics predicts that the average is minus A vector dot B vector. Yeah, good.
Are A and B unit vectors?
Yes. Maybe not even necessarily.
But that doesn't make sense in the equation value of the spin can scale with the magnitude of the direction you choose.
Good. Well, you're right. Sorry. Yeah. So A and B are unit vectors, and we are, I believe, further in the we have scaled things is +1 and -1.
Yes.
Okay. Good. I remember. Oh yes, good. There's an important little note in here that says exactly that, and I skipped over. So, comma where A vector and B vector are unit vectors, and we have scaled the spin operators such that the result of any measurement is plus or minus 1. Thank you. Okay. I'm just looking at the time. It should be fine, but does anybody have a hard cutoff in terms of when they need to go? Hard cutoff is, so you can stay until exactly 11 or this. Oh, great. So I have 24 minutes. I might speed up a little bit, should be fine. All right, on the other hand, suppose that nature obeys a local hidden variable theory. Then instead of states, we should use functions that depend on the hidden variables. And it's these functions that tell us the result of measurements. Even before the experiment is done. Okay. Which is say, i.e., in a probabilistic way. Okay, so define, say, e plus of this a vector and lambda as this function. For the e plus measurement. So a is just telling me it's a function. It's the function associated with the e plus. It has to depend on the direction of the measurement. And it's allowed to depend on any number of potentially hidden variables, or any number of hidden variables. We're just calling it lambda, and we'll only use one lambda for simplicity, but one could generalize this to any number of lambdas in the article still hold. So A depends on the orientation a vector, and also on the hidden variable or variables lambda. Now, since by definition this AE plus a lambda tells us the result of the measurement. And what values can this AE plus take? Exactly, plus minus one. So even though we're imagining that there's some kind of deeper result below quantum mechanics, we know that the measurements are discretized. We can only ever measure plus or minus one. Okay, good. So similarly, we may define, oh gosh, a function b e minus b vector lambda for the e minus measurement. B e minus b perp, not b perp, b vector lambda. Again, only take values plus minus one. By the conservation of angular momentum, how are A and B related? So if I were to ask the question, B e minus is a function of B and lambda, how is that related to the AE plus if I evaluate that at B and lambda? It's minus, exactly. I'm sorry, there was some.
There was some to zero, sorry.
Yeah, perfectly. Perfect. Very good. Question so far, all good. So we can now compute the expectation value in our hidden variable theory, local hidden variable theory, that similarly depends on the A vector and the B vector. And this is going to be some kind of an average over the A function and the B function over the hidden variable. And we're going to allow that there might be a probability distribution for those hidden variables. We just don't know it. They're hidden. But it exists. And so then we average the multiplication of these two functions. So rho lambda is the probability distribution. For the hidden variables. Which we may or may not know. So we're being super duper general here. Maybe there's some deeper theory, we just don't know it yet. Maybe at some point we've discovered this deeper theory and then we know exactly what this rho of lambda is. Yes.
Did about when they commented on when they were writing down this grading one. And also that just by the fact that we assume that A is not a function of B.
By assuming that A is not a function of B?
Of the direction. And B is not a function.
Okay, so you're saying, okay, we could imagine something more general where there's some B vector hanging out here and there's some A vector hanging out here. I'm not sure if what your question is. I haven't thought about this, but
But then just above that, you write B vector inside the A, but I assume you mean something different. You don't mean it depends on the direction chose after the electron. You just choose.
no. So in general, the result of the measurement for the E plus will depend upon the direction that's chosen. We can choose the direction to be represented by the letter A vector, but I could also ask the question, what happens if I put the B vector in for that argument? And necessarily, if I put the B vector in for that argument, then the value of this function A is necessarily the opposite of the value of the B function when the B function is evaluated for the B vector. So A vector and B vector don't have to be the same when we're evaluating this expectation value, but there is a restriction on the functional form of these two functions, capital A and capital B, which is forced upon us by conservation of angular momentum. Precisely, yes. So if I put into the A function the B direction, I necessarily get out minus what I would have gotten for the B function. Yes, good, great. Okay, all right, so rho is a probability distribution. So since rho is a probability distribution, we know that rho must be greater than or equal to 0. And the integral of rho must be equal to 1. Okay. So I would say this is probably equation 2.
And that's over the whole domain lambda.
Yeah, whatever that may be. Mhm. Okay. Oh, sorry, let's name this 1. Let's name this 2. Let's name this 3. All right. So from 1 and 2, we have that this expectation value of A and B. We can simplify it a little bit. We may replace the B function with the A function, but just with a minus sign. I just used this expression here, plugged it into the B here, get a minus sign up front. Okay. Now, let's suppose we make a correlation measurement along a third direction. Call it C vector. Then this expectation value, local hidden variable theory, A, B minus expectation value, local hidden variable theory, A, C. So here's the result for A and B. We get a plus sign here, and this B becomes a C. Now, since the result of any measurement is plus or minus 1, if we square this object, we always get plus 1. And so therefore, this quantity is going to be equal to minus the integral d lambda rho lambda 1 minus a b lambda c lambda a lambda a b lambda. Right? So if I multiply the a vector, b vector through, I get the a vector, b vector for the first term. And then in the second term, I have a b squared, which is just 1. So I've done a little bit of clever footwork. And this expression on the right-hand side is the same as this new expression on the right-hand side. Yes.
I'm confused why you swapped B, when you rewrote the expectation value in substituting both A's plus. Just after from 1 and 2 we have that, yes.
Mhm.
Why did you swap the functions and not the objects?
So we said that b, e minus of b vector lambda is
Yes.
equal to minus a e plus of b vector lambda. So I take b vector here, or not b vector, b function here, and I replace it with minus the a function of the same arguments.
Oh, okay.
Yep,
Sorry.
all good, very good. So I did a little, I'm gonna double check that everybody's okay with relations here on the right-hand side. I've got the a vector, b vector, a vector, b vector. And then the a vector, c vector So if I multiply this through, I've got a b becomes 1, then I have a vector, c vector, so I get the same thing. Bless you. We're okay? Great. So in general, for any, say, b vector and c vector, we know that ae plus b vector, ae plus c vector lambda is equal to plus or minus 1. And so therefore, this quantity, this 1 minus this stuff, this thing is always greater than or equal to 0. Because it's going to be either 0 or 2, which is greater than or equal to 0. And if we consider the absolute value of this different expectation values in our local hidden variable theories, therefore, this is equal to modulus, we'll just, shouldn't say expectation value, I'm sorry, it's the absolute value. Absolute value on the right-hand side. Math tells us that absolute value of an integral is less than or equal to the integral of the absolute value. And that's going to be less than or equal to the absolute value of each object. The a's are plus or minus 1. The rho is greater than or equal to 0. And the 1 minus a is greater than or equal to 0. It's equal to the integral of d lambda, rho lambda, 1 minus a b vector, a c vector. The integral of rho is just 1. And the integral of rho with the two a's is the expectation value. So the key result is the expectation value, the absolute value, the expectation value in the local hidden variable theory for the a direction, b direction minus a direction, c direction is always less than or equal to 1 plus the expectation value of the b direction, c direction. This is super general. The only way, yeah, this is super general. If you assume that math works, this is the result you get. Yes.
Why do we keep the 1 around?
Oh,
wait.
Okay, great. Very, very good. Okay. So let's compare what EQM yields in, I think this is equation 4, right? So i.e. is QM consistent with local hidden variable theory? Well, let a vector be equal to I hat, b vector equal j hat, and c vector equal to 1 over root 2 I hat plus j hat. So our expectation from quantum mechanics, remember, A vector B vector is equal to minus A vector dot B vector, to be proven in the homework. And this is true in general. So for our particular examples, A vector dot B vector, I hat dot J hat, 0. A vector C vector, we get minus 1/2. It's about 0.707. And B vector C vector, also minus 1/2. Now let's compare. EQM, A vector B vector minus EQM, A vector C vector. Is that less than or equal to 1 plus expectation B vector C vector? Well, on the left-hand side, we've got the absolute value of 1 minus the square root of 2. And is that less than or equal to 1 minus 1/√2? On the left-hand side, 0.707, is that less than or equal to 1 minus 0.707, which is about 0.293. So we see that explicitly, that QM predicts a violation of Bell's inequality. So what do? You just go out and you make the measurement. You measure a bunch of spins along one direction, a bunch of spins along another direction, a bunch of spins on a third direction. What is the correlation? And the correlation is in agreement with quantum mechanics and in a violation of Bell's inequality. Nature does not obey a local hidden variable theory.
On the quantum mechanics scale. I mean, like these experiments are confirming that nature obey a local hidden variable theory for these kind of experiments.
Yes. So are you asking, could I get to a smaller scale and that I would then?
Yes, one in which QM, like outside of the domain.
Well, we certainly have never measured anything that suggests there's physics beyond quantum mechanics. Yeah, people have tried very hard to get out of this. And so these are not trivial questions, and there are all sorts of really interesting questions. So you could ask, for example, suppose the experimentalist knows ahead of time what A vector, B vector, and C vector are. Then, well, then A, B, and C are all causally connected. And so you could imagine that perhaps you're not really getting kind of superluminal wave function collapse propagation of information. So people have then created experiments where the directions are randomized. Mm-hmm. And still Bell's inequality is violated. Yeah, so every which way this has been probed, quantum mechanics has shown to be the correct description of nature. But it gets very technical and very complicated. Yeah.
Can you just go up for a second? I wanted to confirm the subscripts.
Let me know where to stop.
For there. Are those all E pluses?
Yeah, everything's an E plus. Yeah.
A little more up. Oh, That's that line, the E minus E
This one?
lower. Yeah, that equals on the right hand side, those are all E plus.
Yes. Yeah,
Because A only has E plus subscript.
Okay. Oh, the
By
one
definition.
above is, oh, sorry. Cool.
okay, cool. I think there's a question here.
Does Bell's actual proof like require them to be?
Oh. I'm gonna go with no, but I'm gonna be tentative about that because integrating over an infinite number of variables makes me nervous. But I feel like it's probably fine, right? I mean, all we are requiring is that whatever integration over the variables is, we require that rho is a probability distribution. So whatever we mean by this symbol, we just say that this is true and that this is true. So I can't off the top of my head come up with some reason why that might mess things up, but I don't want to commit myself because that makes me nervous with it. Yeah. It would certainly go against our idea that we can describe anything. Yeah. Well, yeah, I mean, well, I mean, one of the most incredible mysteries of nature is that we can describe it at all. That experiments are reproducible. Right. So I have not taken a deep dive into the non-local hidden variable theories in a long time. My vague is that the sort of distinguishing between a non-local hidden variable theory and quantum mechanics is highly non-trivial. Like basically, what does it mean for different theories to be different? It means that there needs to be different experimental results. So my recollection is that you can basically mock up a non-local hidden variable theory, which is equivalent to quantum mechanics, but then at that point it's quantum mechanics, but with extra steps. That's my vague recollection, but again, I wouldn't hold myself to that.
So this thing, yeah,
So I'm trying to sort of understand your question. So I think one angle to your question is, why do we have this probability distribution? And the answer is, we know that at least at the level, so we certainly know that we currently are not privy to knowing what the result of a measurement will be. We can only quantitatively predict result of many measurements probabilistically. So we have a determinism in the probabilities, but we don't have a determinism in the exact measurement. So if there's a local hidden variable theory, it has to reproduce that experimental fact that we have. So that's one direction to go in terms of responding to your comment. I think another direction is to ask, and people do ask questions about, like, just deep questions about quantum mechanics. So we've been talking about thinking about a particular system that is being probed by us. And we model that system as a wave function. There's a state in some kind of a Hilbert space. Cheers. That's okay. I'll throw up the video and you can see the rest. And I know I have a meeting at 11. Shoot, who am I meeting at 11? Can I be a little late for that? I can be a little late for that. That's represented by a state. And that state collapses, and we could come back to the question of, how do I resolve sort of this seemingly superluminal influences, and also the question about special QFT, which we can answer in a sensible way. But then you start asking questions about, well, geez, what about the stuff that's making the measurements? That presumably is represented by a state too. And what about the things that are reading the results of these measurements? Presumably that has a state too. And in fact, the entire universe must have a state. And we have this sense of a wave function collapse when we see the result of a measurement. But if the entire universe is in some state, is it continuously collapsing? And if so, how do we think about that? And this leads one to say, for example, the many worlds interpretation, right? That all possible results of all measurements occur all the time, and that the universe just is following some trajectory through that enormous space of possibilities. I feel like that's the best I can do for answering what you've asked so far.
Yeah.
Yeah. Okay, I don't know. Oh, okay. I also didn't know. Before you go, I do want to touch on Tian and Jack's questions, which are very good, and I think we should do them we should touch on them before we wrap up. And I recognize that people might have. Does anybody have a hard cutoff right now? All right, I'll see you later. So in terms of field theory, the fundamental requirement that we have is that measurements at space-like separations cannot influence each other. And that is manifested in requiring that any commutator of any observables at space-like separations is zero. And you can explicitly enforce that by coming back to why the Lagrangian is important rather than the Hamiltonian. In the Lagrangian formulation of quantum mechanics, and especially in quantum field theory, so long as the Lagrangian is local, and so long as our fields obey the spin statistics theorem, which is to say that fields whose quanta have integer angular momentum have commutation relations, and fields whose quanta have half integer angular momentum, intrinsic angular momentum, those have anti-commutation relations. You're guaranteed that commutators of operators of spatial separation are zero. Good. And then the question is, what do we make of this idea that there's some kind of instantaneous wave function collapse, and the interpretation of that there's an instantaneous propagation of information, thus violating special relativity? And the answer is to dodge the question. And to say that there are actually things that we know of in nature which propagate faster than the speed of light. As an example, you could ask the question, how fast does a shadow move? So if I have a light and I move my pencil in front of the light, the shadow that light casts on the wall will move with some velocity, which is related to the velocity with which I move my pencil, and also related to the distance from the pencil to the wall. The larger that distance is, the faster that shadow will move along the wall. And I can take that distance to the wall to be arbitrarily large, and that shadow will move arbitrarily fast. Now, the question is, can I use that superluminal velocity of the shadow to communicate? So could I send a signal to Doron, SOS? And the answer is no. So Doron would see a flash on and off of a light as the shadow passed up and down. But the information about those pulses would be traveling at the speed of light. And so the point is that when Angelia is on Mars and Doron is on Earth, Doron's going to make some measurements. Angelia is going to make some measurements. And they will not know the correlations between those measurements until they communicate the results of their experiments to each other. And that's limited by the speed of light.
This is like more philosophy.
I would actually disagree.
Oh,
I think this is deeply fundamental. Yeah.
it's not philosophy because we can actually just, it's not how you're.
And I think it also, it's very nice in grounding in the physics of there have to be people who, or things that are doing the measurements. And to figure out the correlations, there has to be communication. And so nature does somehow know about the speed of light deep down in the guts of all aspects, even of quantum mechanics. Good. Last questions. All right, that's the end of the course. Thank you so much.